Experiment, I am going to develop and testing a voltage regulator using Zener diode. For this experiment, we require two Zener diodes with 3.6 Zener breakdown voltage, a variable potentiometer, multimeter, and analog port. We don't require for 1 kilo of resistor, so we will ignore this. In this experiment, we are going to do two parts. In part 1, we will create the circuit using LTSpice software. In part 2, we will do the same but on a breadboard. In point 2 of part 1, we have to create the same circuit diagram shown in figure 1. Vs value should be 5 volt, Rs should be 250 ohm, RL, which is low resistor, is variable for this point from 100 ohm to 10 kilo ohm, and a Zener diode breakdown voltage should be 3.6 volt. Circuit on LTSpice software. This is my source voltage, this is my Rs resistance of 250 ohm, this is my Zener diode which have a reverse voltage of 3.6 volt, this is my RL load resistor which have a variable resistance from 10,000 ohm to 100 ohm in a gap of 100 ohm. So this is my output wave of this circuit. The green one indicates the input voltage and the blue one indicates the output voltage of a load resistor. The bottommost wave indicates the output of a load resistor of 100 ohm, then above one is output voltage of a load resistor 200 ohm, then 300 until it reaches 10,000 ohm, which is 10 kilo ohm. As you can see, when my value of a load resistor is 100 ohm, the output voltage is approx 1.4 volt. Then when the load resistor value is 200 ohm, my output voltage is approx 2.2 volt. So as you can see, after 8 wave means when load resistor is 800 ohm, my output voltage is 3.6 volt, and when we increase the load resistance means 900 ohm, 1000 ohm till 10,000 ohm, my output voltage is still constant 3.6 volt. This is because my breakdown voltage of the Zener diode is 3.6 volt. So after 3.6 volt, there is no change in voltage across Zener diode, only the changes in current. And this is because the breakdown voltage of a Zener diode is 3.6 volt. So by this mean we can say that my circuit is a voltage regulator circuit using Zener diode. And why current is increasing? Because this is my voltage source and it produces current which is known as source current, and source current goes and divides into two branches, the Zener diode branch and the low resistor branch. The current of a Zener diode branch is called current across Zener diode, and current across a low resistor. So when resistance of a low resistor increase, the current across a low resistor decrease, and the current across a Zener diode increases. In point 8 of part 1, we have to repeat the same steps 6 and 7, but we will connect one more Zener diode in series. So in total we have two identical Zener diode in series. Circuit of point 8 of part 1, in which I just added one more Zener diode with a breakdown voltage of 3.6 volt in a series. And in this circuit, our new breakdown voltage is 7.2 volt because there is two Zener diode in a series, and the breakdown voltage of these two Zener diode is now added. So our new breakdown voltage is 7.2 volt. So let's see the triangular wave of input voltage and also output voltage. This is the triangular wave of input voltage, and this blue one is the triangular wave of output voltage of a load resistor. So let's zoom it and see. As you can see, there is no slope between the triangular wave of output voltage of a load resistor as we seen in the previous circuit, and also this triangular wave of output voltage of a load resistor, the blue one, is not reached the breakdown voltage 7.2 volt because our value of a load resistor is from 100 ohm to 10 kilo ohm. So when the load resistor is the 10 kilo ohm, our maximum output voltage is approx like a 4.65 volt. So to reach a breakdown voltage 7.2 volt, we have to increase the value of a load resistor more than a 10 kilo ohm, like suppose 100 kilo ohm to 100 kilo. So this is why there is no slope in between the wave of output voltage. In part 9 we have to repeat 6 and 8 points. Just we will replace Rs of 250 ohm with Rs of 500 ohm resistor. 9 of part 1, in which I just replaced the value of Rs from 250 ohm to 500 ohm, and everything else is same like a previous circuit. This is my graph of the circuit, in which green line indicates the input voltage and the blue line indicates the output voltage of a load resistor from bottom value of load resistor is 100 ohm till 10,000 ohm, which is 10 kilo ohm in the gap of 100 ohm. In point 10 of part 1, we will use one Zener diode with Rs 500 ohm and RL of 1 kilo ohm, and we will add one more voltage source. In 10 of part 1, in this circuit I use the two voltage source and Rs, source resistor value of 500 ohm, one Zener diode which have a reverse voltage of 3.6 volt, which is a breakdown voltage, and a load resistor which is a value of 1000 ohm, which means 1 kilo ohm. Let's see the input voltage and output voltage of this circuit. This is the input voltage of this circuit, and the blue one is the output voltage of the circuit. As our breakdown voltage of the Zener diode is 3.6 volt, so the maximum output voltage of the load resistor should be 3.6 volt. In part 2, we will do the same what we did in part 1. We will just do everything same on a breadboard. We will use ADLM board as a voltage source in part 2. This is my part 2, in which I have to create the same circuit which I created in part 1 using LTSpice software. This is my circuit of a figure 1 as shown on the screen. The green resistor is RS, which have a value of 220 ohm. I have to take a resistor of 250 ohm, but I don't have that, so I have taken the resistor of 220 ohm. This is a potentiometer, which is a load resistor. The value of this potentiometer is 1 kilo ohm. I have to take the 10 kilo ohm of load resistor, but I don't have that, so I'm taking the load resistor of 1 kilo ohm. This is my Zener diode, which have a breakdown voltage of 3.6 volt. This is my ADLM 1000, which I'm using as a voltage source. The orange wire is connected to a channel A, gray is connected to a ground, and white is connected to a channel B. As showing on the screen, this green triangular wave indicates the input voltage, which have a range of 3.8 volt to 4.8 volt at a frequency of 100 Hz. The lower green wave indicates the output voltage of a load resistor. As now the output voltage of a load resistor is 0 volt, because my value for load resistor is now current is 0 ohms. As I increase the value of a load resistor, my output voltage will increase. As showing on the screen, the wave is going upwards because I'm increasing the value for load resistor, so my output voltage is increasing, but it will increase till 3.6 volt because breakdown voltage of a Zener diode is 3.6 volt. And after that, when we increase the value of a load resistor, the output voltage of a load resistor will remain constant at 3.6 volt. So Zener diode start allowing current to flow in one direction in a reverse bias condition. So the current of a Zener diode start increasing as we increase the load resistor, but the value of output voltage of a load resistor will remain constant at 3.6 volt. This is my second circuit, in which I use a RS of 220 ohm, and I use two identical Zener diodes which have a 3.6 volt of breakdown voltage, and this is a potentiometer of 1 kilo ohm, and still I connected the same pins of ADLM 1000 as I connected the two same diodes in a series. So breakdown voltage of the both diodes will now add, and my new breakdown voltage is 7.2 because 3.6 plus 3.6 is equal to 7.2. So to conduct current in a reverse bias condition in a Zener diode, my output voltage of a load resistor should be greater than 7.2. So Zener diodes start conducting a current in a reverse bias condition. So as we see on the screen, currently my load resistor value, output of the load resistor is 0 volt, approx 0 volt. So when I increase, when I increase the value of a load resistor, my output voltage will increase. It will increase till it reaches breakdown voltage. After that, only the current of a Zener diode will increase.